So far, to use the central limit theorem, you needed to have an estimate of both the expected mean of a distribution and the expected variance. But if you have nothing to go on, if you are estimating the parameters of your model, then actually you can only determine the mean, you can only make an estimate of the mean, and the estimate of the variance depends on how good your estimate of the mean is. So if you want to use the central limit theorem for estimation of your distribution, then this doesn't work out very well. We already defined x bar as the running average over our experiments, over our series of stochastic variables. And from now on we will refer to x bar as the sample mean of our experiments. That's to contrast it with the expected mean, which is the expected value of the distribution behind it. Now what Slutsky did was, instead of only looking at the distribution of the sample mean, he also considered the sample variance, which is defined as follows. You take the value of the stochastic variables xi minus the sample mean rather than the expected mean, and divide the sum over all of these stochastic variables. You square them and divide the sum by n minus 1. Not by n, but by n minus 1, because you need at least two measurements to be able to speak of a variance. Now, as an exercise, you could try to prove that the expected value of s squared, which is the stochastic variable that keeps track of the sample variance, is indeed equal to the expected variance, which is the variance of x, which we usually denote as sigma squared. What Slutsky has shown is that not only the variable Zn converges to a normal distribution, but also a slightly adapted version of Zn prime, in which he replaced the sigma by the square root of s squared, so by the square root of the sample variance. And that means that in order to use the central limit theorem for hypothesis testing, you don't need an estimate of sigma squared up front anymore. You can just use the measured value of the sample variance. Just like we did at the end of the video on the central limit theorem, we can now take a series of outcomes of experiments and test it against a hypothesis, a model, that this experiment has a distribution with expected value mu. We don't care what the distribution exactly is, that's not what we're testing for. We only assume that the distribution also has a defined variance, that is a kind of distribution that has a defined variance, but we don't need to know what that variance is. To perform the test, we sum up the outcome of all the experiments, divide by the total to get the sample mean, and we also compute the sample variance over the entire sequence of experiments. And then we compute the value of z prime n defined by Slutsky. If we now compare that value to the normal distribution, we can determine the probability of finding a value at a distance greater than or equal to Zn prime. And that probability is the probability that our experiment actually has an underlying distribution that does not have an expected value mu. So that's the probability that our model is actually wrong. Now, if we want to do our experiments properly, we should not decide afterwards whether a percentage that we found is good or good enough to reject our model. We should actually determine this up front. So usually we say up front we want to test our hypothesis that this model holds with a confidence level of 99.9%. And to be even more precise, statisticians usually make a distinction between two kinds of hypotheses. There is the null hypothesis, which is the statement you want to believe is true and you're trying to refute, but you will accept it unless you find evidence against it. And there is the alternative hypothesis, which is the statement you're gathering evidence for. Our null hypothesis in this case is that the outcomes are distributed with an expected value equal to mu, and the alternative hypothesis is that the outcomes are distributed in a different way. So a confidence level of 99% means that we will only accept the alternative hypothesis if we are 99% sure that the model is wrong. Next, you determine the bounds that coincide with this confidence level, and for that you have to invert the distribution, for which traditionally we use lookup tables, but you can also use MATLAB to do the same computation. After you've determined the bounds within which Zn prime should lie, you can draw an interval, a so-called confidence interval, around the sample mean and determine whether your expected value lies within this confidence interval or outside. If it lies outside, you reject the hypothesis that mu was indeed the expected mean of the experiment. If it lies within, you accept it. Indeed, you draw a confidence interval around the sample mean and not around mu, because you can use this method also to estimate the parameter mu rather than refute or reject a hypothesis. Because after drawing a confidence interval around the sample mean, you have an interval in which this parameter should lie. Now, if you need to display the outcome of your measurements in a report, then often we use a dot in a graph to display the outcome of the mean of the measurements, and two lines above and below it display the confidence interval. And in the caption, you somewhere mention what the confidence level is for which you've drawn the diagram. Now, of course, if the confidence level becomes higher, if you choose a higher confidence level, if you want to be 99.9% sure that the actual mean, the expected mean, lies within your confidence interval, then the confidence interval becomes larger. If you choose a lower confidence level, then your confidence interval can become smaller. Yes, there is something dangerous going on here. This dot and two lines is easily confused with a different kind of plot, which is called the box-whisker plot. And the box-whisker plot is actually intended not to give you an idea of a sample mean and where the actual expected mean of a distribution is supposed to be, but it is intended to give a whole more detailed view of the distribution in the measurements that you found. In a box-whisker plot, there is a line in the middle which not shows the mean, but shows the median of all the measurements that you did. So it's the 50-50 point. 50% of your measurements falls above this line, 50% falls below this line. Then the box around it shows the 25% quantile, which means that 50% of the measurements falls inside this box. 25 falls below the upper part of the box, and 25% falls above the lower part of the box. Then there is lines on top and below, which are the 12.5% quantiles. And then there is a line on the top and on the bottom, which show the maximum and minimum outcomes of the measurements. So a box-whisker plot really shows a concise distribution of how the measurements were made, while this dot and confidence interval, the mean and confidence interval, well, they show a rather different characteristic. When you write a report, you should use a box-whisker plot when you want to give the dry results of your measurements and leave them for interpretation to somebody else. And you should use a confidence interval when you are comparing the results of your measurements to some hypothesis.